Okay.
Sorry, I don't buy like $15 notebooks that are plastic. Doesn't have a brand on
Okay. I'm ready for spring break. If you didn't know, the power was off in this building from Tuesday all the way until Saturday afternoon. That was number 3 on my crisis list for last week. That's it. Coronavirus is number 4. If you feel like you're sick, I always record things, but with people on self-quarantine and all of that, we're supposed to be very flexible. So if you feel like you're going to get everybody sick, then don't come to class. We'll figure something out. Okay, I have your exams. I posted the answer key. You can take a look at it if you need to go over it. We can go over it. I have to put midterm grades in for everybody by Wednesday, which I will do probably today, so that you'll have midterm grades. But midterm grades are just that, midterm grades. And there's no quiz today, but there probably will be for Wednesday with reagents. So I'll give you that information. Okay, so where were we at a long time ago, it seems? We were talking about benzene, and that's going to be sort of the theme of this week. I did put all of the stuff for Wednesday and Friday up because I have to do that so that people who aren't here can see that. So we're going to talk about adding things now to the benzene ring. And so we talked about that before break. But basically what I'm going to do is I'm going to add an E+. How I generate that E+ is going to be different reagents that we're going to have to learn. And what's going to happen is that the E+ is strong enough to add to the benzene ring, so I'm going to end up adding my E with my H. And I don't know what that crackling is, but it doesn't sound good. And so I'm going to end up forming the carbocation, which I can then take that carbocation and delocalize it around the ring. But if I added a nucleophile to that carbocation, I would destroy the aromatic ring. I can't do that, and so what I'm going to do is instead I'm going to end up losing the H+. And so when I lose the H+, I'm going to end up replacing or substituting an H with an E. So this is electrophilic aromatic substitution. So we talked about some of the reagents that we can use, which at this point you want to have, your 3x5 cards sort of made up for those, but just to go back so we're all on the same page, the first thing is HNO3, H2SO4. That will generate an NO2+. The NO2+ then will add to the benzene ring, bless you, so that I can make nitrobenzene. Next one was to add a halogen So we can use Br2 or Cl2 along with AlBr3, AlCl3, FeBr3, or AlBr3. So in other words, iron bromide. So iron or aluminum trihalide, that will generate a Br plus or a Cl plus. Those will add to the benzene ring, so I will basically end up halogenating the ring. That was reagent set number 2. Okay. They are the same. It's 8 o'clock. It's gonna take a little time for you and me to get back into this. So that was reagent set number 2. Then the next was to add an SO3H positive, SO3H plus to the ring. So if I want to add an SO3H plus, I'm going to take my benzene ring, and now I'm going to add SO3 and H2SO4, which is the H2SO4 is going to protonate the SO3 to form HSO3 plus. The HSO3 plus is going to add to the ring, and so that's how we make what's called a sulfonic acid, which we talked about last week being, or 2 weeks ago then, saying, okay, we can change that OH to a Cl, and that makes our polyl chloride. Then the final group, and this is where we're going to pick up, is the idea of saying, okay, if I want to add an alkyl group to the ring, I need to make a carbocation. We talked about all the different methods that we could use to make a carbocation. So just some of those were, if we take an alcohol and we add acid to it, we can make a carbocation. If we took something with a double bond in it and added H plus to that, we would add the H plus Markovnikov-ly to make the carbocation. That would then add to the ring. And the more traditional electrophilic aromatic substitution way of doing this is to take an alkyl halide, add H plus to that, or sorry, not add H plus to that, but add aluminum trichloride or iron trichloride. And you can do this with a bromine as well. Add those, and what will happen is the aluminum will take off the chloride so that we can generate our carbocation that way. That would then add into the ring so that we would make our alkyl benzene, and that is called Friedel-Crafts, in this case alkylation, because anytime I add an alkyl group to a molecule, it's called an alkylation reaction. So this is a traditional way of adding the carbocation. Now there are some complications to that, there are some extensions to that, and that's where we're going to pick up today. And then we're going to talk about the pattern of substitution, and then get more into some of the ways we can change over our groups once they're on the ring. Okay. Now the first thing about Friedel-Crafts alkylation is that all of the rules about rearrangements are still in play. So you can't have carbocation rearrangements with Friedel-Crafts. One of the big limitations on Friedel-Crafts is this: you cannot add a straight chain to a benzene ring. So what happens is, if you try and add propyl chloride to benzene to form N-propylbenzene, it will not work. And the reason that it will not work is because what will happen is that if we think about the aluminum or iron chloride, when the chloride is pulled off, you might say, well, if I'm forming a carbocation by reacting the alkyl halide with aluminum trichloride, if I'm forming a carbocation, how can I do this with any primary system, or how can I do it with methyl or ethyl that don't form carbocations? And the issue is not that it forms a carbocation. What happens is, as the aluminum, so if I think about the aluminum pulling off the chloride, at some point, as it pulls the chlorine off, you end up with enough delta positive charge on that primary carbon that it will then add to the ring. So you never truly form a primary carbocation, you just form enough delta positive charge for it to then become electrophilic and add to the ring. But what happens with a straight chained alkyl halide is that if I take this if I take the CH2 next to it, what will actually happen is we'll end up with a hydride shift, so that the hydride will shift over to the primary position and kick off the chlorine. As it's being pulled off, that hydrogen will shift over, and in that case what we'll end up with is we'll end up with a secondary carbocation, and the secondary carbocation will then add to the benzene ring. So whenever you try and do a Friedel-Crafts alkylation with a prime or with a straight chained alkyl halide, you will always end up not with you will not end up adding the straight chained alkyl group. Instead, what you will end up with is you will end up adding the rearranged secondary carbocation. So in this reaction of propyl chloride plus benzene ring, you're going to end up with isopropyl benzene and not propyl benzene. So that's something that that we have to keep in mind. And there is a way to work around this, but it's going to require 2 steps instead of 1. Okay, so that's a limitation on Friedel-Crafts. You can get rearrangements. Now, I will always tell you when you'll get rearrangements, except one case. This is the case where I will not tell you to rearrange. I will expect you to know that if you add a straight chained alkyl group that you will get a rearrangement. But other than that, I would tell you when to do a methyl shift or a hydride shift. Okay, so that's the one time that you need to know. All right, so there are some limitations to Friedel-Crafts alkylation. How do we get around that? I need to add a propyl group unrearranged to a benzene ring. How do I get around that? And the way we get around that is by adding a carbonyl group to the ring. First of all, when you add a carbonyl group to the ring, that is called Friedel-Crafts Isolation. So the acyl group would be, okay, instead of adding propylbenzene, let me add this acid. This is a carboxylic acid chloride. Anytime there's a chloride or bromide on the molecule, just add aluminum or iron trichloride to it. It's going to rip the chlorine off and it's going to leave a carbocation. So in this case, I would react this with Okay, I'm going to go to a new slide here. So I'm going to add aluminum trichloride to this. And again, the chloride is going to be pulled off by the aluminum. And I'm going to end up now with a carbocation. And now that carbocation is what is called an the fact that I'm not swearing tremendously right now is just last week. Just a hangover from last week. So that's an acyl carbocation. Now it's stable because I could take this pair of electrons and I could move it there and write the resonance hybrid of having a triple bond to the oxygen and then putting the plus charge on the oxygen. But the carbocation is what's going to add to the ring. So you may have seen that when we did mass spectrometry and we were writing the different resonance structures that we could get for an acyl carbocation after we did what was called alpha cleavage. So the acyl carbocation is stabilized by resonance, and it will then add to the benzene ring. So if we took our benzene ring and we said, okay, let's add our benzene ring with acid chloride and aluminum trichloride, what we will end up with then is we will end up with what is called a phenyl ketone. So we end up adding the acyl group to the benzene. So this is Friedel-Crafts Isolation. Again, similar thing. You want to add a carbon group to the ring, put a chlorine on it, react it with aluminum or iron trichloride, it'll make the carbocation. The one glitch in all of this is it can't be straight chained, because then it will undergo a hydride shift and you'll add the more stable carbocation. Now, why is this important? Well, it turns out that if I wanted to add that propyl group unrearranged to the benzene ring, I could then take my phenyl ketone and I can do what is called reduction on it. So if I take my phenyl ketone, I can treat it with two different reagents that will take the carbonyl group and it will turn it into a CH2 group. Not an OH group, but a CH2 group. So this is a full-blown reduction. I think if you went back and looked in your notes, when I brought up phenyl ketones before, I asked, well, what reagent would we use to turn that into an alcohol? And then after a considerable amount of page turning and time, we said, oh, lithium aluminum hydride, sodium borohydride would reduce it down to the alcohol. These are different reagents that'll take it all the way down to the CH2. So the two sets of reagents that we can use are, first of all, N2H4, KOH, and heat. That is hydrazine, potassium hydroxide, and heat. That is one set of reagents that we can use. The other set of reagents that we can use is a zinc mercury amalgam, HCl, and also heat. So these are two different sets of reagents that will take the carbonyl and make a CH2 group out of it. So the final product then is our propylbenzene that we would like to add. These two reagents have, they do have names, but you're going to want to write the reagent instead of just the name. So one of these is, this one is called Clemmensen Reduction, and this one is called Wolff-Kishner. So Wolff-Kishner reduction is with hydrazine. Clemmensen reduction is with the zinc-mercury amalgam. So you mix zinc and mercury together and it forms basically a new material, which is called an amalgam. If you're old enough where they used to fill teeth with, instead of ceramic stuff, they used to use mercury amalgams. Mine are probably all gone at this point, but they were at one point mercury. So, which may explain a little bit sometimes of the insanity that I go through. But we can do that. So the idea here is that, bless you, if you want to add a straight chained alkyl group to the ring, the first thing we need to do is to add the appropriate ketone and then do a Wolff-Kishner Clemmensen reduction down to the straight chain. So it's a two-step process to add a straight chain to the ring. You can't do it all at once. And those reagents are something that you're going to have to remember. All these reagents are going to have to remember, because when we get to Friday, then what's going to happen is we're going to start talking about, okay, here's a benzene ring. I want to put these groups on the ring. What reagents do I do? And more importantly, what order do they go in? And so that's what we're working towards here, is how do you convert a benzene ring into your molecule that you want? All right, so that's Friedel-Crafts Isolation along with reduction. And the goal is to add a straight chain alkyl group to the ring. Now you can add anything you want. We should probably say, well, where did this acid chloride come from? The carboxylic acid chloride came from a carboxylic acid. And still may be a little bit too early to ask this, but what reagent could I use to convert the carboxylic acid group into the acid chloride? We could use PCl3, SOCl2. The one thing we cannot use is HCl. HCl will not work. But SOCl2, PCl3, PCl5, all the bromine equivalents, that will convert the OH into a Cl. So that's where the acid chloride comes from. Right? You can add any carboxylic acid. It doesn't have to be straight chained, it could be branched. But the idea is that if I add the straight chain carboxylic acid chloride, then I'm going to reduce it down, and that's how I add a straight chain to the ring. So those are Friedel-Crafts Alkylation, Isolation, NO2, SO3H, and halogens. Those are our first 5 reagents that we can add to a benzene ring. So I might decide on Wednesday's quiz to give you those and have you write in the reagents, because the quicker we can get them in here, the better. Okay, everybody still kind of with me? Kind of like, wait, it's the first day after break. We move on. Now, the next thing is, reacting a benzene ring with all these different electrophiles is boring. because I got 6 hydrogens to choose from. It doesn't matter which hydrogen I add to the ring, or what hydrogen I substitute for. So let's make things a little bit more interesting. Let's say we have a group, which I'll call G. Let's say there's a group on the ring. And now I'm going to add my electrophile to that group. Substituted ring, the mono-substituted ring. Well, what's going to happen? Now I have an issue, because where does the electrophile go? Does the electrophile go ortho, meta, or para to that group? And at this point, you might be hoping it's random, so that we just go, well, it's random, let's move on. It's not. It's not random. It's going to depend on the group. So the group is what is called a director. It tells the electrophile where to go. The electrophile does not have a choice. The electrophile will go where the group tells it to go. So the group then is our director group. And now what we have to do is now we have to go back to groups that donate electron density and groups that withdraw electron density. And we not only have to do that, but now we have to put them in order. So, putting those groups in order, and I've done this in the past, I'm going to add one more group so that we have a full 10. First are nitrogen groups. They are number 1. Then oxygen groups. Then another benzene ring. Then alkyl groups. And our H is our baseline. So what we find is that those groups, nitrogen down to R, they all cause the reaction to be faster than benzene. So these are what we're now going to call activating groups, which means they are electron donating. They're electron donating groups. And you might say, well, why are they activating? Why would they make the ring go faster? Because in this reaction, the electrophile is the electrophile, and the ring is the nucleophile. How do I make the ring more reactive? Make it more nucleophilic, which means push electron density into the ring. Once you push electron density into the ring, then it will react faster. Which group pushes the most electron density? Nitrogen, then oxygen, then benzene ring, then alkyl group. Why nitrogen, oxygen, and benzene ring? Because they push by resonance. Why alkyl group is last in the electron pushing? Because it's using induction. And induction is weaker than resonance. Okay. So all of these are activating electron donating groups. We use the activating term, which I know people asked about before the last exam. Activating now just means electron withdrawing. It means that ring is going to react faster, but it's also going to tell me where the group is going to tell the electron, the E plus, to go. Right, bottom, we're going to start with something that is the weakest electron withdrawing, which means induction. So that is halogen. Then all carbonyl groups. Then C triple bond N. Then NO2. And then finally I'm going to add a 10th group, which is that if you have 4 alkyl groups attached to a nitrogen, it makes that nitrogen have a positive charge. That NR4 group, the bottom one looks like this. That ammonium, that's an ammonium group. And it's technically going to withdraw electron density by induction. So we have halogen, carbonyl, C triple bond N, NO2, and then our NR3 plus group. And those are ranked according to most electron withdrawing. So halogen, least electron withdrawing, NR3, most electron withdrawing, but the real issue with putting an NR3 plus group on the benzene ring is that then there's going to be a positively charged group on the ring, and you're trying to react to positively charged electrophile. Those two positive charges are going to repel each other, and so for the most part, if you make if you put an ammonium group on the ring, it will not undergo electrophilic aromatic substitution for the most part. So this group from this list from number 1 to number 10 is what you're going to have to remember as well. So you're going to have to remember these groups from number 1 to number 10, simply because we need to know that in order to decide where's the electrophile going to go. Ortho, meta, para. These are called deactivating groups, which means they are the electron withdrawing groups. So again, pulling electron density out of the benzene ring is going to make it less nucleophilic, which is going to slow its reaction down. So if you want to do electrophilic aromatic substitution and you want it to be very reactive and very violent, use nitrogen. Put a nitrogen group on the ring. If you want to push it, if you're going to have to use heat to push the reaction to go, you put nitro groups on the ring. So our breakdown is hydrogen is the baseline. Everything above hydrogen is activating. Everything below is deactivating. So what people found was this. When they started doing these reactions, these are not anything theoretical. These are actually, if we do the reaction, this is what we find the reaction rates to be. What they found was that for the activating groups, they direct the electrophile to go to the ortho and the para positions relative to that group. So when you're reacting a benzene ring with an activated group on the ring, it will react faster, but that group will tell the electrophile go to the ortho position or go to the para position, so you're going to get a mixture of ortho and para products. Okay? Those are called ortho-para directing groups. That's what the activating groups do. Well, there's a yin and a yang of organic, right? I mean, it's always the opposite. So what does the deactivating groups do? The deactivating groups give very little ortho and para products. Instead, they direct to the meta position. So the deactivating groups tell the electrophile, go to the meta position relative to me, the directing group. So we have to know this list in order to know what the products of the reaction will be.
Sorry, I'm having trouble hearing you.
Is that mine? Is that Siri or Alexa? They have the same voice though, don't they? Anyway, that's why we need to know this, is because we need to know where those groups are, where the groups direct to. Okay. Is everybody still kind of with me here? This is like a lot in the first day back, but it'll work out, I guess. So let's do an example. Okay, we take toluene, which is methylbenzene, and we add to it nitric and sulfuric acids. The first thing in solving this problem is I need to know what is my electrophile. So when I react nitric and sulfuric acids, what E plus do I get? I'm going to get an NO2 plus. And so now where is that NO2 plus going to go relative to the methyl group? Well, it's going to go ortho and para, because to answer that question, I need to look at the group on the ring. It's a methyl group. Is methyl activating or deactivating? Methyl group is activating. You'll know that by Wednesday. And then the methyl group says, nitro group, you go here and there. And so I'm going to get two products of this reaction. I'm going to get the NO2 group adding ortho, and I'm going to get the nitro group adding to the para position. So I'm going to get a mixture of those two products. At this point, what I would like you to, when you're writing the products of these reactions, is if it's an ortho-para director, you're going to write both products. At some point, what we will do is we will invoke sterics, but not this moment. At some point, we'll say, you know what? There's a huge group on the ring. Fitting that group in the ortho position is not going to be as favorable as putting in the para position. Or if I'm adding a huge electrophile, I'm going to say, well, that's probably going to go to the para position, not the ortho. But that is not now. Now I'm going to ask you to write both. Okay. Now, sometimes when I asked this question in the past, people would say, no, the nitro group is going to go meta. And if you're a person who's going to confuse what I say now, this is what you do not do, then you might want to just plug your ears and not hear this. But sometimes, if people make mistakes initially, they confuse the group with being the director. The group does not direct. So if you're looking, you're going, but nitro is a meta director when it's on the ring. When it's the electrophile, it goes where the group on the ring tells it to. The group on the ring is an ortho-para director. It tells the nitro group where to go. The group itself, even though some of these groups are directors, it does not self-direct. It's told where to go. Okay. So, toluene plus an NO2 group produces ortho-para directors, or produces ortho-para products. Now, what happens if there's two groups on the ring? Let's say I want to add another NO2 plus group to that ring. And I could add another NO2 plus group to this ring as well. How do we handle groups with more than one? Or how do we handle with benzene rings with more than one group? The easiest way to handle this is, and I think the book still uses a method that I used back in circa 2000, if I remember correctly. They talk about, well, let's take each individual group on the ring and let's see it where it directs to. And if they direct to the same position, that's where the nucleophile is going to, or where the electrophile is going to go. Or if they're pointing in opposite direction, who wins? And that's the way I used to teach it. And then a student, and I still remember the student, they're now a doctor somewhere. But I remember she goes, do we really have to do that? And I'm like, well, of course, I just told you we have to do that. And she's like, well, wait, why don't we just go with the group that's highest on the chart? Because best case scenario, the groups are pointing the same direction. Worst case scenario, it's going to win. So why don't we just identify the group that's highest on the chart and then use it as the director? And I'm like, that's genius. And so I haven't gone, that's the way that I've done it since. So see, you can make genius points. They're still out there. You just have to find them. So in this case, which is higher on the chart, methyl or nitro? Well, this is why we have to memorize the chart, so that we know. And in this case, methyl activating, nitro deactivating methyl wins. But if it was methyl versus nitrogen, nitrogen would win. So the group that's highest on the chart is the director. Regardless of whether they direct to the same position, opposite position, doesn't matter. Find the group that's the same, that's the highest on the chart. That's going to do the direction. You might say, but what if you have two of those groups? Okay, then they're both directors. If they direct to the same position, you get those products. If they direct to opposite positions, you get a whole mess of products. All right, methyl's going to direct. Methyl is orthopara, which means it's going to direct the nitro group here and here. Why doesn't it direct to the other side? Because there's already a group there. So I'm going to get two more products out of this one. I'm going to have the NO2 group here, and I'm going to have the NO2 group down here. So those would be my two products of the reaction of the ortho nitrotoluene with more NO2s. Then I want to continue on. I want to add a third nitro group to the ring. Again, I look at the ring. I'm just going to do it on the molecule on the left. The methyl group is still the highest on the chart. It's going to direct orthopara to itself. The ortho positions already have nitro groups, so that means that methyl group is going to point to the para position. So the final product of that reaction is going to be to put that third nitro group on the para position relative to the methyl. And the reason I use this example is because if we add nitro groups to any of all these products, what I'm going to end up with is the same product, which is trinitrophenol. Which I think I talked about before. So if you want to make trinitrotoluene, that's how you do it. You start with toluene with a methyl group and you exhaustively nitrate it, which is TNT then is different than nitroglycerin. And nitroglycerin was, I think, Alfred Nobel's. Dynamite sticks are nitroglycerin mat with clay. TNTs, they both explode. So the problem here is making this compound. The first nitration is going to be a piece of cake because this is an activated ring. The second nitration is going to take a little bit of heat because now I've got a deactivating group on the ring, so it's not going to react as quickly. I put two nitro groups on the ring. It's going to take a little bit more heat to put that third nitro group on. Here's the balancing act. Enough heat to get the nitro group, not enough heat to blow it up. So being a worker in a TNT factory early on in the industry would have been a hazardous operation. Because when you're doing the heating, it's got to be just right. That's where you sit on a three-legged stool so you don't fall asleep. Sort of like when you're boiling tree sugar down to make maple syrup. You always sit on a three, not three in a triangle, three in a normal position, so that way if you fall asleep, you hit the floor and wake up again before everything burns down. So this is how we handle a molecule that has multiple groups on the ring. Just choose the one that is highest on the chart. But it is doing the direction. The group on the ring is directing. Okay. Now, the reasoning for why activating groups, I'm going to come back here for just the last thing. The activating and deactivating groups, there is one exception to all of this. So activating groups are all orthoparas. Deactivating groups are metas except one. Halogens are orthopara directors. Halogens are orthopara, not meta directors. And the reasoning behind how these groups are activating and how activating groups are orthopara, how the deactivating groups are meta directors, and the reason why a halogen is orthopara but deactivating is actually in the video for today, and I'll briefly summarize that on Wednesday. But the halogen groups are orthopara. They're the exception to the rule. Okay. So if that doesn't, what I'd ask is take a look. There's a video in there for today. You can sort of fast forward to that spot. If it doesn't make sense, then I can summarize it and go over it again. I did put the video for Wednesday, all the different reactions that we're gonna do, and I'll summarize those on Wednesday as well. So if you could take a look at that or in the book. For Wednesday, then we will have a quiz. The quiz will be the reagents so far that we've learned, and also then the number 1 to number 10 chart. If I get a chance today, I will write that chart out and put it on Canvas. But again, you looking at it isn't going to have nearly the impact as if you write the chart out yourself. And when you're writing the chart out, I would say write the groups out, whether they're activating, deactivating, whether they're orthopara, including this, and then meta directors, because that's what I'm going to ask you to write out on Wednesday so that we can begin to get that order. The only thing there's only going to be one group on the chart, and that's hydrogen at number 5. You're going to have to fill in the groups from number 1 to number 10. Tell me whether it's activating or deactivating. Tell me whether it's orthopara or meta. So that, along with the reagents, I know it's going to be a lot, but that's okay. We need to get that in place. Okay, so that's for Wednesday, and I'll remind you